This is 2.2, Limits Involving Infinity, Part 2. Your objectives for this lesson are to determine horizontal and vertical asymptotes, apply properties of infinite limits, and to use end behavior models to describe behavior of functions. So first of all, you see that if f of x outgrows all positive bounds as x approaches a finite number a, then the limit of f of x as x tends to a, let me add that in here, is equal to infinity. So basically, if your y value is getting very large as x approaches some value, then the limit at that x value is infinity. And if f of x outgrows all negative bounds as x approaches a, then the limit of your function as x tends to a is equal to negative infinity. Okay, so this would be an example of that first bullet point here. You can see that x is approaching 0, so 0 would be your a value here. And your y values are becoming increasingly large. It looks like it might stop around here, but these actually keep going up. So we have a limit at infinity, and this is a vertical asymptote here. So before we're looking at horizontal asymptotes, this is a vertical asymptote. So let's look at this quickly. We have f of x equals 1 divided by x, and the limit as x approaches 0 from the right of 1 over x is equal to infinity. So this is the graph that we were looking at in the previous lesson, this one. So as x approaches 0 from the right, going this way, so traveling this way, we see that our function is going towards infinity. And as we approach from the left towards 0 going this way, we see that the y value is approaching negative infinity. So the limit, the left-hand limit, is negative infinity. And that tells us that x equals 0 is a vertical asymptote. Since we have the x approaching 0 and that limit is at infinity, it's a vertical asymptote. The definition of a vertical asymptote is the line x equals a is a vertical asymptote of the graph y equals f of x if either the limit of x approaches a from the right of f of x equals plus or minus infinity, or the left-hand limit of f of x equals plus or minus infinity. So if either one of the limits, right or left-hand limit, of the function is equal to plus or minus infinity, you have a vertical asymptote. Example 1. Find the vertical asymptotes of f of x equals 1 divided by x squared. So what we're going to do first is look at the limit as x approaches 0 from the right. So right-hand limit of this function. And I'm going to pull my calculator up to look at this quickly. So calculator, going to 1 divided by x squared. Oh, and this is our graph. This was the one that I showed you first during this lesson. So if we look at the right-hand limit, it's approaching from the right over here. Going up, we see that that is equal to a positive infinity. If we look at the left-hand limit, that also is a positive infinity. So if you approach 0 from the other side, so over here, that's also positive infinity because they're both going up. And since x is approaching 0 and we get this infinite limit, we can conclude that x equals 0 is a vertical asymptote. Okay? So, and you could also say, since the right and left hand limit are equal, you could also say here that the limit of x approaches 0 of this function is equal to infinity. But this is your answer. This is your limit. Example 2. The graph of f of x equals tan x equals sine x over cosine x, remember that's just a trig identity, has infinitely many vertical asymptotes, one at each point where cosine is 0. Okay, so let's look at that. Let's see. Tan x, and our window for this will be negative 2 pi by 2 pi for your x's, and negative 5 by 5 for the y's. Okay, and each of these vertical lines that you see here is an asymptote. That is not part of the line that is being graphed. That is an asymptote. So, and you can see that those asymptotes kind of repeat in a regular pattern there. And those are where cosine equals 0. So if you remember from the unit circle, cosine equals 0 at pi over 2. That's the first time on the unit circle where cosine is 0. So if we do x is pi over 2, you see there's nothing written there for the y. It is undefined. And then on the unit circle, cosine is 0 again at 3 pi over 2. Over 2. And that's undefined again. So we know that this is going to be at x equals pi over 2. X is 3 pi over 2. And those are 1 pi away. So basically anytime you have an odd integer in front of this, you're going to have an asymptote. So what we can conclude about this is these would all be our a values from that definition of a limit. And if a is an odd multiple of pi over 2, and that's what we talked about here, coefficients 1, 3, 5, 7, it'll keep going, then the limit as x approaches a, so right hand limit, of tan x is negative infinity, and the limit, the left hand limit as x approaches a of tan x is positive infinity. Okay, so looking at our calculator, you can see if we are coming in from the right, we're moving down, and that does go towards negative infinity. If we're coming in from the left, we're moving up towards positive infinity. Example 3. Let f of x equal 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6, and g of x equals 3x to the 4th. Show that while f and g are different for numerically small values of x, they are almost identical for the absolute value of x large. Let's look at this graphically first, because this is pretty easy to see graphically. So 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6. And g of x, we'll put that in at y2, we have 3x to the 4th. Our window for this, we'll look at a small window first, because we're looking at small values first. Negative 2 by 2 for x's, and negative 5 by 20 for our y's. Okay, so we can see the two graphs, and you can see that there is a large gap between them. You can see that gap. It is noticeable. But if we go back to the window and we adjust it so that we are zoomed quite a bit out, so negative 20 by 20 for x's, and still negative 100,000 by 500,000 for the y's. Okay. Looking at those, I mean, I can see that I could see the second line when it graphed, it made the line look a little thicker. But other than that, I see one big U shape here. There is no noticeable difference on my screen right now. So when I zoom out, when I'm looking at the bigger picture of things, there is no difference. Those graphs look identical to me. When they're zoomed in, I can see a difference. So that's what we're looking for right here, graphically. If we wanted to confirm this analytically, we can. So analytically, or algebraically, the limit as x approaches plus or minus infinity of f of x divided by g of x equals, we're going to write the actual equations in here. So f of x is 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6, and this is over 3x to the 4th. Okay. And this, we're going to use a quotient rule here. Remember, you can break this up into 1, 2, 3, 4, 5 different fractions. So I'm going to do that. So we have 3x to the 4th. Again. Okay, let's simplify. These both cancel, so that's a 1. Those go away. That's just an x to the 1st there now. Those go away. This is x squared. These become a 1. That goes away. This is x cubed, 2, and that's a 1. Okay, so we get limit of 1 minus 2 over 3x plus 1 over x squared minus 5 over x cubed plus 2 over x to the 4th. Okay. And if you were to plug an infinity into each of these, if you divided 2 by the largest number in the world, then you are basically left with nothing. Same here and here and here. So the limits of all of these 4 are 0. So we get 1 minus 0 plus 0 minus 0 plus 0, which gives us 1. And this was 1, remember, because the limit of a constant is itself. So your limit is 1. Since that the limit of the ratios is 1, that essentially means that those, when you're looking at the big picture like we did on the graph, are pretty much the same function. And this brings us to our next topic, which is end behavior models. Okay, so definition of an end behavior model. This is the formal definition. You can read it here, but basically an end behavior model tells you what a function looks like as you look at the ends where x is approaching positive or negative infinity. And you have some rules here for finding the right end behavior model and the left end behavior model. So they won't always be the same, but you can use these to find functions that approximate the behavior of whatever function you're looking at the ends. That's what we're going to do next. Okay, so example 4, let f of x equal x plus e to the negative x. Show that g of x equals x is the right end behavior model for f. So when you're looking at the right end of the function, it eventually starts to look like y equals x. And h of x equals e to the negative x is a left end behavior model for f. So when you're looking at the left side, it looks like e to the negative x. So let's use our definitions from the previous slide to show this. So the right side of this, remember our definition says that we have f of x divided by g of x. So the limit as x approaches infinity of f of x divided by what we think this behavior model is equals x plus e to the negative x over x. So we're going to take the limit as x goes to infinity of this, and if you divide x by x, you get 1, plus the limit of e to the negative x divided by x. So that should be 0, but let's confirm graphically quickly. So e to the negative x divided by x okay, and you can see that that goes to 0. So I'm on the line here, but it's really hugging the axis there. So that will be a 0 as x goes to infinity. So we get 1 plus 0, and we have a 1. So remember that for this to be the right end behavior model, this should equal 1. It does equal 1, so that checks out. So the right hand of the graph, as you zoom out, will look like y equals x. Now the left hand of the graph, or left behavior model, left end behavior model. The limit as x approaches negative infinity of f of x divided by h of x. So our original function, limit of the original function, x plus e to the negative x, over what we think is that end behavior model e to the negative x. And if we break it down, we have x divided by e to the negative x plus 1. I'm hoping that this is a 0, but let's look at the graph to confirm. So y equals x divided by e to the negative x. And as we look towards the left, towards negative infinity, you see that the y value here is approaching 0. So the limit of this is 0, plus the limit of a constant is 1. So we get 1, and that checks out also. So those were the right and left end behavior models of this graph. Example 5. Find an end behavior model for f of x equals 2x to the 5th plus x to the 4th minus x squared plus 1 all over 3x squared minus 5x plus 7. And really, when you're looking at these big, long polynomials like this, the term with the highest exponent is what determines the end behavior of the graph. So on top, this is going to behave like an x to the 5th graph. On the bottom, if we were just looking at the bottom, it would behave like an x squared graph. But we have the ratio of these. So we're going to look at 2x to the 5th over 3x squared, which is just 2/3. And if we're subtracting the exponents, we have an x cubed in the numerator. So this is our end behavior model for this function. Okay, shortcut, very nice, very easy. Part B, g of x equals 2x cubed minus x squared plus x minus 1 all over 5x cubed plus x squared plus x minus 5. Again, we're looking for the terms with the highest exponent, so it's 2x cubed on top, 5x cubed on the bottom. It's not always the first term, so you should definitely always double check that. So we have 2x cubed over 5x cubed. The x cubes cancel, so our end behavior model is y equals 2/5. Okay. I should probably write y equals up here also. So y equals example 6. Does the graph of f of x equals 4x squared minus 3x plus 5 all over 2x cubed plus x minus 1 have a horizontal asymptote? If so, what is it? Okay. So we're going to look at this from an end behavior perspective. So the end behavior of our graph, remember our shortcut that we just learned. We have 4x squared over 2x cubed. So this is 2 divided by x. And since the graph overall behaves like y equals 2 over x, let's find the limit of this as x goes to infinity. So the limit as x tends to infinity of 2 over x. Now again, if you divided 2 by infinity, you would essentially get 0. So this limit is 0. And therefore, based on our previous definitions, we have a horizontal asymptote at y equals 0. You might also remember your shortcut. So if the x with the highest exponent is in the denominator, then your horizontal asymptote is automatically 0. And that would be a good shortcut to know also.